Okay, so thanks for staying back in 5:15. And so the problem is parametric shortest paths in planar graphs. We'll define what our shortest, I mean, you all know what our shortest path. We'll define the parametric shortest path problems and then specifically in planar graphs. Okay. So let's start. So you have a graph, a directed acyclic graph, okay, and two special vertices S and T. And in this particular example, all the edges are directed from left to right or from down to up, right? So there are 6 possible paths in this graph, and you want to find out what is the shortest path, right? And I thought since it's 5:15, so people need some more motivation to stay back, and what could be bigger motivation than true love? So there is this guy, and he wants to get to his loved one, and he wants to get there as soon as possible. Okay. So now all these edges have weights, and think of these edges as roads, okay, and these as traffic junctions. So this is the amount of traffic on each road. So 60 means there is big traffic. This means there is very little. And he wants to find the best way that he can get to her. And as you can see, the best way is P4. In this case, P4 is the shortest path. And that's it. There's nothing new here. This is just a normal shortest path problem. Okay. Now let us look at parametric shortest path. So in many scenarios, the traffic on a given road might not be fixed. Okay. It is dependent on a variable like time. So here everywhere you see a lambda. So think of lambda as time, and the traffic varies as per the time of the route. Okay. And now we want to find out the shortest path. Again, the problem is the same. However, now this term doesn't even make sense because all the paths are linear functions of lambda. Okay, let me mention this. So they can be in general polynomial functions, but for the rest of this talk, we'll be looking at only linear functions. Okay. So the paths are all linear functions of lambda, and these are the cost of their path. And now, what is the shortest path? However, what we can do is we can assign a specific value of lambda, and then we can ask this question. So what is the shortest path at g of lambda? So at lambda equal to 0, it is P2. At lambda equal to 1, it is again P2. At lambda equal to 2, it is another path P1, and we could go on. Okay, so this is the description of the problem, and what we want to find is the number of times this shortest path could change. So as you saw, from 0 to 1 it did not change, but from 1 to 2 it did change. Right? So yeah, this is the description of the problem. Is everything clear so far? Good. Okay. So now let's pause.
What is the definition of shortest path? I mean, for every lambda, it's clear.
Yeah. So when you fix a lambda, these become real numbers, and then you find the shortest path. That's it.
And you want to find the total modes, find the number of times.
Yes, number of times it changes. Yeah. So it could be that you change lambda, but the shortest path still remains the same. At some point, it does change. So we'll see what happens. So you vary lambda from 0 to infinity. It could also be minus infinity to infinity. It doesn't make a difference. And we plot the cost of the path on this graph. Okay. So since everything is linear, the cost of a path is also a straight line. So this is the path P1. Similarly, P2, P3, P4, P5, P6. Okay. All these are linear. And we denote a shortest path sequence as the shortest paths in this case are P1, P2, P3, P5 and P6. So there is no P4. Note that at lambda equal to 0, P1 is the shortest path. In fact, continues to stay the shortest path till this point. Over here, P2 takes over, okay? Then P3 takes over and so on. But P4, however, it's far above, so it's never the shortest path, okay? And in general also, this is just for a specific example that we just saw, but in general, this will always be a piecewise linear concave function. It looks like a concave, it's not a smooth concave function, but it's piecewise linear because all the shortest paths are linear in lambda, right? And as I mentioned, what we are interested in is the number of breakpoints. So these are breakpoints where one shortest path leads to another. And we are interested in the number of times once the shortest path changes. And we formalize this by this quantity phi. So what is phi here? Yes, it does look like that.
What is the motivation of like getting a number of breakpoints?
Yeah, good. So mostly in this dynamic programming setting, what you have is you are given the traffic cost, and while all this is coming in, you calculate the shortest path dynamically, right? But in case the shortest path is very small, for certain graphs, suppose it's, the number of shortest paths is very small, you could pre-compute them and store them in memory. Exactly. Instead of calculating them at each given time. And you'll see how it can be actually quite good.
Sorry, I have
So,
one
yeah.
question, sir.
Yeah.
So, is it also not possible that the value of the change from lambda, the value of the shortest path will be the same, but it will be a different path which achieves? Is that not possible?
Yes, so two paths could have the same line, the same equation, that's possible. But what we are looking at is breakpoints where, okay, so what we do is order each path lexicographically, and if two paths have the same cost, then we choose the lowest one. Okay. So we are looking at these breakpoints essentially.
So the value of the path changes what it is.
Yes. Yes. Is that your question?
Yeah.
Okay. Yeah. Okay, so what is P formally speaking? So you are given a graph and a set of linear functions, then P is the number of breakpoints, as we just said. And what we are interested in is what is the maximum value this P could take over all possible graphs on n vertices. Okay? So what you do is take all possible directed acyclic graphs on n vertices, all possible linear weight assignments to them, and choose the one which has the maximum number of breakpoints. And what is this number phi of n in terms of n? Can we even bound it in terms of n? That is the question. And the answer is yes. Okay, let's see how. So first let's prove a very trivial upper bound. Okay. So firstly, is this number even finite? Could you have a sequence like first you have P1, then P2, then P1, then P2, and P1 and P2 and so on forever? Could P1 and P2 alternate with each other? And the answer is no, they could not, because these are concave functions and these are straight lines. Once the path P1 is lost, lost to P2, it will never ever come back to the shortest path. Is this clear? They are not curves. So if they were curves, then P1 could possibly come back somehow. But since they are straight lines, once P2 starts dominating P1, it will dominate it forever, for as high as lambda. Okay, so this scenario is not possible. So far this just implies that it is finite, and this implies an upper bound. So this is the statement that I was saying. A shortest path once abandoned cannot be used. So once P1 is lost, it will never be the shortest path again. Once P2 is lost, it will never be the shortest path again, and so on. And this yields a trivial upper bound of n factorial, because worst case the number of paths in any graph can be as big as n factorial, which is exponentially. Is this clear? But this is not a good upper bound. Obviously, you want something better. Okay. So we can again use the same statement that the shortest path once abandoned cannot be used. However, note that this holds true for subpaths as well. So here, what did we say? We use this statement for ST paths because we are only looking at paths starting at S and ending at T. However, if you choose any two vertices X and Y, again, their shortest paths are also linear functions in lambda, and we could use this property repeatedly. And that's exactly what Gusfield did in 1980. And he proved an upper bound which is much better than exponential, which is quasi-polynomial, which is n raised to log n. Okay. And then the question is, can you still do any better? This is still quite big. And people thought, this is such a weird number, why would this possibly be a lower bound? And surprise, it was actually a lower bound. Oh, sorry. I lost. Okay, there is a surprise will come later that this is a lower bound. Okay. So, first of all, let's try to understand what are alternation-free sequences of paths. Okay. So, okay, what are we looking for here? Suppose someone tells us there is some graph, and this is a sequence of paths. He's given us the complete description of all the 8 paths. He's given a sequence of 8 paths and given a complete description. Even without looking at the graph, can we tell him that this sequence is not at all possible? We just know the vertices and the edges in this path, in this graph, and without looking at it, can we say, no, this sequence is not possible? So let us see how. Firstly, note that none of these PIs are the same, they are all distinct. What we'll show is, just again using the same property, we show that there is an alternation between these two vertices, B and D, in this graph. Okay? So all the paths start from S and end at T, but restrict yourself to only those paths that have both B and D. Okay? So look at only these paths, P1, P3, P4, P6, P8. Okay? These paths have both B and D. And now let's look at the BD path. Okay? Here the path is BCD, and that's fine, nothing wrong with that. This is okay. Here the path is again BCD, which is fine. this path is not abandoned, so it is fine. You are still reusing the same path. This is allowed. Over here, you are abandoning the path BCD for a new path BGD. This is also allowed. Here, again, you are using BGD. This is also allowed because you abandoned BCD, but you haven't yet abandoned BGD. So this path you can again use, but here it is an alternation because BCD was an abandoned path, and now you are reusing that path. And is that clear? The definition of an alternation. So to be more precise, you can also say the three paths P1, P4, P8 constitute a BD alternation in this sequence delta. So P1, P4, and P8. So P1 has BCD. Sorry. Was there a question? Yeah.
Like he asked the question, you said that sorting sections are C and Z are same because
Sorry, this has nothing to do with the actual graph on the this thing. They'll have some sort of this thing. Somebody just gave you these paths. Okay. You can just by looking at these paths, because you know BCD, whatever linear function it had, it was abandoned for BGD. Now BCD can never be a shortest path. So BCD was some straight line. Okay. Then BGD came across. Now BCD can never come back. Is this clear? Yeah. Okay. So this is proper definition of alternation tree sequence. And yeah. And this is Gaussian's upper bound. So how exactly does he prove his upper bound? Okay. What he does is he defines this term f of n comma k. What is f of n comma k? Let f of n comma k be the maximum length of an alternation tree sequence of paths in an n vertex graph where the paths are restricted to at most k edges. Okay. You have a big alternation tree sequence and you want to provide an upper bound on this. So you restrict yourself to those paths which use at most k edges from the graph. Okay. So firstly, the base case is f of n comma 1 is 1 because any two vertices there is either an edge between them or there is not. Okay. And this is the reference, and we just quickly see why this reference holds. So you have a vertex S, okay. You have a vertex T, and we are restricting ourselves to paths of at most k edges. So for now, let k be an even number. Okay. So fix a particular vertex V as your middle vertex. So all these paths are of length k by 2 at most. These are of length k by 2. Right? And there could be many paths here, P1, P2, so on, till Px. Suppose there are x paths here. Here also there could be many paths, Q1, Q2, so on, till Qx. Okay. Now suppose your first ST path, it has to take one subpath from here and one subpath from here, right? So it could look like this, P1, Q1. Your next ST path cannot be this exact path, so it has to change either on the left or on the right. So next path maybe, suppose it changes on the left, it goes like P2, Q2, right? Now P1 is abandoned, it can never be used again, right? Suppose your next path uses P2, that's fine, P2 can be used again. But over here, it continues to use Q2, right? So now, sorry, what did I say? Yeah, sorry. So now P2, Q1. Now it continues to use P2, but it abandons Q1. So now Q1 is crossed out. What could also happen is it abandons both of them. You could use a P3, Q3, in which case there are two things crossed out. So note that at each step, at least one of them is crossed out. So, sorry, Q by. So the total number of paths can be at most x plus y. So if this, by induction, if this is f of n comma k by 2, the total is twice of f of n comma k by 2. And this was for a fixed vertex V, and there are at most n vertices, so there is a factor of n multiplied over. Okay. So you just evaluate this recurrence at f of n comma and you get Gaussian control. Okay. Yeah, finally, now the lower bound, and here is the surprise finally. N raised to log n. The upper bound that we got is also in fact a lower bound up to constants in the exponent. Okay. And this was a result by Patricia Carstensen in 1983. 18 years later, in 2001, Ketan Mulberry and Prajit Shah showed the same lower bound. However, the their edge weight. So, okay, how do you show a lower bound? You have to demonstrate a graph in which this n raised to log n paths are actually achieved, okay, which has these many breakpoints. So in their description of the graph, the edge weights have polylogarithmic bit lengths. In Carstensen, she makes no such claims or doesn't even try to make them. Okay. So yeah, and finally we come to planar graphs. For planar graphs, Nikolova, Kellner, Brand, and Nissenmacher, they showed that this quantity is at least omega n, and note that this quantity is quite small in the sense we are dealing in terms like n raised to log n, so linear in n is not a very good upper, a lower bound. And however, for a special, so PL here stands for phi of n restricted to planar graphs. Okay. And these guys, in just 2 years back, they showed for a restricted case of planar graphs known as series parallel graphs, this is also an upper bound. So what people expected is that the upper bound for planar graphs will be something like polynomial in n. Like, so Nikolova, who was an author in one of the authors in the previous slide, in fact, it was conjectured in this paper itself, informally, and in her PhD thesis in 2009, she conjectured that for planar graphs, this quantity will be bounded by some polynomial in n. And surprise number 2, we showed that this is also in fact n raised to log n with the same bit lengths as what was there in the Munmule chart. Okay. So, why was this assumed to be polynomial? Is because it was thought that because planar graph has this nice grid-like structure, you can never have more than a certain number of paths that will come up as shortest paths. Okay, and basically, what they tried to show is that to upper bound the number of alternation-free paths. To upper bound the length of the maximum sequence of alternation-free paths in planar graphs, and that will be an upper bound on this number. So now we see that that intuition was in fact not true. Okay. So what are we going to see? We'll see a planar graph on these many vertices. So don't worry about the numbers for now. And we'll see many alternation-free paths such that so we'll see a sequence of alternation-free paths that is of size n raised to n. Okay. And the corollary of this is if you substitute n is equal to log n, you get a graph on poly n vertices and alternation-free sequence of length n raised to log n. Note that this is still n raised to omega log n. You can make poly n, take capital N equal to poly n, you get a constant in the exponent which is n raised to omega log n. So as long as the vertices is not n but still bounded by some polynomial in n, we won't bother counting them exactly. Is this clear? Okay, so the description of the alternation-free paths is actually quite nice. So you want a sequence, right? You want a sequence of paths, and turns out they just correspond to a normal sequence of numbers. So take the m base n numbers of m digit series. So in our example, take m equal to 3 and n equal to 4. So take all possible 3-digit numbers in base 4. So the smallest is 0, 0, 0, and the largest number in base 4 is 3, 3, 3. Okay. What we show that is each number over here corresponds to n paths, and since there are total of n raised to m numbers, there will be n raised to m plus 1 paths. Okay. So how does each number correspond to a path? So now imagine these paths are drawn on a cylinder. Okay. Let me explain. I haven't explained the graph. So this is a layered graph. The vertex S is connected to all vertices in the first layer, and T is connected to all vertices in the last layer, and all edges are directed from left to right. Okay. And between any two layers, you have a complete bipartite graph, but it is drawn slightly differently. How is it drawn? So these I will call them as the zero edges because they just map to the very next edge. The next two edges, I'll call them as the one edges in the sense they map to the edge, map to the vertex, one vertex above it in the next layer. Okay. And think of these two things drawn on a cylinder, in which case these things curve and they meet at the other end. And I have just opened the cylinder and I'm showing you over here. Okay. So this last edge over here, it goes from here and then comes back from here. Is this clear? Okay. These are your two edges and these are the three edges. And this happens between any two consecutive layers. Okay. Now, I promised you these graphs will be planar. However, we've noticed this is not planar. I mean, they are intersecting like millions of times. So, not millions. So what are we going to do to make it planar? So just consider one such layer and we planarize it by doing this. Okay. So just add few more vertices in each layer. Again, the number of vertices we are adding is polynomial in n, so it will not affect the lower bound too much. And whenever you take a zero edge, for example this edge, it just corresponds to this path. You take the one edge, it corresponds to a path taking one slanting edge and two straight edges. This corresponds to two slanting edges and one straight edge, and so on. Okay. So my entire construction, I will describe it on this graph, and later on you can always planar it by using this gadget. Is this clear? Fine. So
There's more than one path for the weight one edges.
yeah. So right now these graphs are unweighted. I'm just describing my paths. I can take whatever path I want.
So there were multiple choices, you just chose to pick one.
Yes. Yes. That's it. Okay. So now let's look at a number. I promise that each 3-digit number corresponds to some path. So how does it correspond to a path? So you take the least significant digit and place it in the middle. Okay. What do I mean by in the middle? So for this edge. Now all these edges, they see the number 2, so they connect themselves to 2 edges, right? So what is the 2 edge? This guy connects to the guy in the next layer, which is 2 steps above him. Similarly for every guy, so these are all parallel. Now consider the next least significant digit, place it in the middle of this section and this section. You get something like this. And now these are 0 edges, so you can just connect them straight away. And 1, you place it in the middle, I mean wherever there is space left. And you get all of these are 1 edges. Okay. And that's it. So notice that all of these are vertex disjoint paths. When I say vertex disjoint, ignore S and T, they are obviously all connected to S and T. But other than that, they are all vertex disjoint because they are essentially following the same sequence. So they are all parallel to each other. And that's it. So when you arrange, these are 4 paths, or these are n paths in general. And when you arrange these numbers from 0, 0, 0 to 3, 3, 3, the sequence of paths that you get turns out that they are actually alternation. And these are on a planar, I mean, right now they are not on a planar graph, but using the gadget I described earlier, you can just planarize them. Is this clear? Fine. So this kills all the intuition you had earlier. We had earlier that planar graphs cannot have lengthy alternation-free sequences. But still we have not assigned edge weights. This does not prove that the parametric complexity of planar graphs is quasi-polynomial. Because we still have to assign linear edge weights such that these particular paths in this particular sequence are realized. Right? So in fact we won't do that. We won't exactly do that. We'll do something else. Okay? So we go back to the proofs of Patricia Carterson and Mulmule and Shah. What they do is something like this. Okay? Instead of one starting vertex S, you have B, capital B starting vertices S1, S2, S3, S4, so on till S capital B. And you have capital M ending vertices instead of T, where M is some number roughly 2h to M into T. Okay? And this is basically your graph, which I have not described here. And so this is a layer graph as we described in the example. It's not exactly the same, with a slight difference. And sorry, this number is wrong. Okay, it's capital B. And how the proof goes is, when we draw that graph, plotting lambda on the real line, right? The real line we divide it into roughly n raised to m disjoint intervals, such that within each interval, a particular path drains as the shortest path. Okay? In the sense, when lambda lies within this gap, there is one fixed path that is the shortest path. When lambda comes into the second gap, there is another path. Third gap, there is another path. And once you can define this for n raised to m different intervals, you are done. You just set n is equal to log n. Okay? And how this graph is exactly built is recursively. So let me describe the construction. So at level m minus 1, so okay, what do these two numbers m minus 1 and b stand for? M minus 1 stands for the level of the recursion, okay, and b stands for the number of input vertices. So we want a graph at the level m, we will look at graph at level m minus 1. So all these 3 graphs are at level m minus 1. So you start with b input vertices, okay, and then you reverse the same graph and you attach it to itself. So you attach this graph to itself. So now this had s input vertices. So this has S output vertices because it's just a mirror image of the graph. Then you connect it using something called a link gadget. This I'll describe shortly. And then this is also coming from the previous level of induction, but a bigger graph. That graph was on B input vertices. This is on B plus N input vertices. Okay. So what exactly is happening here? Okay. So this is the final graph that we desire. It looks complicated, but it's actually quite simple. So all these graphs are at level 0, okay? At level 0, you just have these straight edges. So this is your graph for v equal to 0, 1 input vertex, 4 input vertices, 7 input vertices, 10 input vertices. At the next level, you take this graph and you reverse it. So the reverse of an edge is the edge itself, and you attach it using this link gadget to the next graph. Here again you do the same, take this graph, reverse it, attach it to the next graph, and so on. So at the last layer, what is happening? You took this entire graph at the previous level, which is this, right? You reversed it, which is this till here. Okay, this is the reverse of the graph, and you attach it using this link gadget to this graph. Okay, fine. So what exactly? So all the magic is happening in the link gadget. What exactly is the link gadget, and how is it happening? So this was the Mulmule-Shah link gadget, and it was a very dense bipartite graph. Obviously, it has a lot of edges crossing, and they have this edge weight function where WB, B plus R means when the Bth input vertex maps to the B plus Rh vertex over here. Okay, this was their function. Our link gadget is also similar, but what we do is you draw it on a piece of paper, okay, and with where these points are dots and these things are lines, and you draw this portion at a distance of 1 unit, okay, and wherever a couple of lines intersect, you put a new vertex there. Again, the number of new vertices is polynomial, and so it doesn't really matter. But turns out you have to reassign the edge weights, okay. After reassigning this edge weight, what you do is, now there are new edges created, you distribute this edge weight in proportion to their lengths. So earlier this was a single edge, right? Now this has been broken up into 1, 2, 3, 4 edges, and you assign all of these edges the edge weights in proportion to what their actual length is over here, right? And that's it. So what problems could arise? Earlier, as Ruhani pointed out, it was up to us whatever path we choose. But now, earlier this was, if you want to go from here to here, it's a single edge, this is the only path, right? But now there are weird paths that could arise, but we would still like this to be the shortest path. So we assign our edge weights in a certain way. We assign our edge weights in such a way that those new spurious paths that are created will never actually be shortest paths. In the sense, shortest paths in the new graph will correspond to edges in the old graph. Okay. And okay, what is this link gadget? This is basically what I just said earlier. Okay, sorry. So this is what I just said earlier. The shortest path from B to B plus R is still the straight path. Okay, and any deviation from this path incurs the cost of at least 1 unit. And a vertex. Yeah. Also, another important thing is, it should not happen that earlier a vertex was not even reachable, but because of this planarization, suddenly that vertex becomes reachable. And that actually is the consequence of how these graphs are actually built. If you observe that there is no way a vertex could actually reach a vertex which it was not able to reach earlier. And yeah, so that's it. Those are the properties of the link gadget, and basically this left portion is planar from the induction hypothesis. This is planar from the induction hypothesis. This is also planar from the induction hypothesis. And the link gadget we have planarized, and once you attach these graphs together, the final graph is planar. Okay. Now in the remaining 15 minutes, I'll just briefly describe how they actually assign edge costs. So this is the description of the graph, but you still have to assign edge weights to the edges of the graph, right? In particular to the link edges of the graph. Oh, by the way, I should have mentioned this earlier. So all these straight edges that you see have cost 0, okay? Everything that is going on is in the gray area, it's called the link edges. Those are the only edges which have actual cost. These are just straight edges. These are 0 weight edges. Okay, so how do you assign the edges? Right, so the shortest path, so look at the left graph, okay? Let me draw this. So the construction was something like this, right? You have a graph on the left, let's call it G left, G middle. And then over here you had some link gadget, okay, doing something. And it attaches to a new graph, G right. Now, G left by the induction hypothesis as n raised to m minus 1 intervals. Okay. Furthermore, it also comes with a shortest path. In the sense, if you are in this interval, this is your shortest path. Anywhere, if lambda lies within this range, this is your shortest path. If lambda lies within this range, this is your shortest path. I'm sure. Okay. Similarly, for this other graph, Gm minus 1 comma, this is b plus m, it has its own shortest path, right? And now you want to somehow merge these two graphs together so that you get n raised to m intervals. Okay. So now, okay, the edge costs are defined in such a way that the intervals are exactly the same. Okay. These two graphs are different, but their intervals are exactly the same. And what our proof methodology will be this: we pick a particular interval, okay, and we subdivide it into n intervals. And we do this for each interval, and it turns out to have n raised to m intervals. Okay. Now, how do we do this? Again, I won't be able to go into the details of the calculations, but basically this is our induction hypothesis. Okay. I'll just let it remain there, and I'll explain what is happening. So, you have these three graphs. Okay. Now, so this is the combination of Gn and Gm. Okay. This is the link carry. Okay. And this is Gi. So basically they all have the same set of intervals. Okay. And he also has the shortest path. So now notice that I'm drawing multiple edges. Earlier I do just one edge for each this thing. I'm drawing multiple edges because if you note in the induction hypothesis, the cost from the bh vertex is the cost from the zeroth vertex plus something which is not dependent on lambda. So all these shortest path costs have the same coefficient of lambda, hence they are parallel. So those lines are basically parallel. And we need this. So what exactly happens in the link edges? Link edges look something like this. Okay. They are all diverging. They are all, obviously they are also linear functions of lambda, so they are straight lines. And they are all diverging. So what actually happens within a specific, so let's concentrate on one interval, right? Let's concentrate on, oh, this is the second, okay. Okay, let's concentrate on this third bracket. Okay. Now, the way the edge costs are defined or designed is in such a way that okay, the first path that will be taken will be the one with the worst edge of the link carry. Okay. So you will take, so within this guy, the first path that you will take will be this. Okay. And here, what you take is this guy. Oh, sorry. So this is. So initially you take the smallest guys over here, okay, and over here you take the top guy. But you note that these edges are diverging. At some point, this guy's cost will be too bad. He can't continue to take that. At that point, you start taking some other combination of edges. Then you go for this edge, then you go for this edge, and so on. And eventually, as you get all combinations of these edges, this one interval will split itself into an interval. And this will happen for each of these intervals, and these n intervals will become n square intervals. Sorry, this part wasn't, I didn't go into the calculations or anything, but at the end of the day, this is what is happening. Right. So, yeah, that's it, that's the proof, or whatever I said. Yeah, so I can actually say, how much time do I have? Okay, I can say one more thing. One is that how do we actually design this graph? Right? I mean, so from a particular input vertex, you have some shortest path, okay? And the property is that all these shortest paths are parallel, as it was in the earlier example. So from this also, what is the shortest path? It has to be parallel to this, right? Now we have to prove that whatever shortest path is taken over here, the shortest path in this entire graph will be just a reflection of this, in the sense, when you reflect this, and initially this is not clear why it should be true. But notice that the cost between any shortest path and property number 1 and a non-shortest path is some large, think of C as some large number, okay? So, which means, so firstly, if you are starting from B and ending up at B, then it is clear you must take this path, okay, this optimal path. Suppose you are not, suppose you are ending up at some other vertex C, okay? Look at the shortest path, the reflection of the shortest path in C, okay? Now, note that whatever optimal path, suppose it started at B and ended up at C. If it went through this vertex, then it must have taken a non-optimal path here, right? And if it went through this vertex, it must have taken non-optimal path here, which is not possible. Hence, the optimal path is still a reflection of the original path, okay? And the second property is that when you are finally attaching the graph GR, right? So using the link array, you are attaching a graph GR over there. And how are you actually achieving that? Okay. And the point is, even after the attachment, these paths continue to remain the shortest paths. Why? You have these equations, right? These are plotted as a function of lambda. There is some shortest path curve. What you do, you multiply every edge weight by an extremely large constant capital K, okay? And that will just scale up the entire graph by a huge amount capital K. The number of breakpoints will remain the same. The shape of the plot will also remain the same. It just be scaled up by that much. So if all the paths differed in by some number C, now will be some huge number K, and then it won't even matter what paths were there in the other part of it. Okay. So another way, you had two or three different jobs to take. One of them offered you like 2 lakhs, one of them offered you 5 lakhs, one of them offered you 8 lakhs. And you want to know which job to take because you don't know later how much bonus you get. But suppose I tell you all the bonuses are within 10,000. Then you won't even bother, you just take the highest one. And that's basically all that's happening. So by this restriction, we can ensure that we can only consider paths over here. And about paths over here is what I described using the earlier graph. That completes the proof. So yeah, that's it. We also show that, so far all in our entire proof, the edge weights were polynomials of degree 1 in lambda, right? And we want to explore what happens, what about d of lambda, where d is some fixed constant, say degree 5 or something. And turns out it's not much more. It's obviously more than what it is for degree 1. And so here you have n raised to log n plus some constant by Gauss-Fields upper bound. And what we show, it is again n raised to log n plus something which is a big super constant, and this is an extremely slow going inverse Ackermann function which Electro had pointed out. And this is alpha n plus some constant t. Okay. And and the proof is actually quite simple. It uses Gauss-Fields idea and the fact that 2 degree d polynomials can intersect in at most d points. Earlier it was 2 straight lines can intersect in at most 1 point. And there are these nice combinatory objects known as Davenport Schindler sequences. We use them and it yields this upper bound. So yeah, that's all. Thank you.
So any ideas regarding what might happen if you take non-polynomial functions?
Yeah, so it's not been considered, but you could have infinite, like you could have a graph on 4 vertices that has infinite number of these things. So you could have S and T, right? And these weights are 0 and 0. And these weights are sin lambda and cos lambda. And the graphs look like this and like this. And every time one shortest path is overtaking the other.
Any kind of periodic functions might lead to that.
Yes.
So if it's monotone, then it's probably, let's say.
Sorry?
If the function is monotone, then probably.
Doing monotonically increasing.
I mean, yeah. No, or
So you could, so this function is monotonically increasing, right?
okay.
You could have something like this.
But then a straight line could cut it.
Okay.
Yeah, so this has not been explored for other more complicated functions.
Do have so essentially, so you would view this as if you look at this graph, source code represents, you think of each path as set of these linear functions. Now you are adding them up, but if I consider them as monomials, then that should actually tell you the number of distinct monomials that you would have in a
You're talking of degree. I mean,
I think what I'm saying is
I
to me.
Answer. Okay, you're saying the particular edges on the this thing could be some. Yeah, I haven't thought of it.
No question. Okay, it's time to close it.